This is section 9.2, and we're going to talk about something called using properties of matrices. So hopefully you watched 9.1, you know what transformations are, and that we're focusing on translations to start. So translations just when you move a figure. And we're going to talk about something called matrices. So let's go ahead and get started on that. And let me pull up my notes. So what is a matrix? So a matrix is, if you've taken Algebra 2, you'll know what it is. A matrix is actually a rectangular arrangement of numbers in rows and columns. So I don't know if you've ever seen this on your calculator or you've ever, run across this anywhere, but down here, these are examples of matrices. So this is kind of something new for a lot of people. It's the first time that they've seen it before. Basically, a matrix is a way to store a lot of data. So in what we're going to do, we're going to use pretty small matrices, but really the purpose of a matrix in higher level math is that we can put a lot of information into a matrix, and that can help us solve higher order problems and problems that have a lot of data. But what we're going to talk about today is we're going to talk about a matrix that can help us represent points and actually can help us to use a matrix to do translations and rotations and reflections. So this chapter or this section is actually going to be really key for some of the kind of coming up sections. So just make sure that you really understand that. So a matrix is actually made up of rows and columns. Nothing too shocking there, right? So a row, right? A row is represented here. Oops, it would help if I can draw. This is the first row, and this is the second row. Okay, so this particular matrix has two rows, and then, so we call these the rows. You'll see that here, rows. Okay, and then we also have columns, so you can think of columns like on a building, right? And this particular matrix has three columns. And I'll U, M, N, S, there we go, has three columns. So understanding the size of a matrix is the first important thing. So a matrix is just a rectangular arrangement of numbers and rows and columns. So this particular matrix has two rows and three columns, so we would call this a 2 by 3 matrix. So we name the number of rows and the number of columns, and that's what size our matrix is. Just to kind of give you a feel down here, this matrix has two rows and two columns. So this matrix is a 2 by 2 matrix. Okay, this is again 2 rows and 3 columns. This is a 2 by 3 matrix. And so we can have matrices that are much bigger than that as well. But those are probably the ones that we're going to deal with. So why do we care about these matrices? What do they help us out with? Well, we can actually use a matrix to represent a point or a set of points more easily. So do you remember, if you just watched that last video, or you haven't watched it in a little bit, we have like all of these, data points. And so this is an easier way to represent that data point all in one spot. So let me zoom in a little bit here. Okay, so hopefully you can see this. This is a polygon. This is a quadrilateral ABCD that we have graphed out here. We can use a matrix to represent a point or a polygon. So if I wanted to represent point A right here as a matrix, point A, the first thing to know is, where is point A? So point A is at -3, 0, right? So we know how to do coordinates. We've done that for a while. If I wanted to represent point A as a matrix, what we do when we have a matrix is we usually treat the top row as our X and the bottom row as our Y. So if I wanted to represent point A as a matrix, I would say point A is at 3, 0. That kind of makes sense. So this is one piece of data. And if you want to, think about it, you say point A is at -3, 0, and can kind of think about that as point A. Okay. So that kind of makes sense for one point. Where matrices help us out is what happens if we want to represent a whole quadrilateral. Okay, so we want to represent quadrilateral ABCD. So think about this. Each column of my matrix is going to represent a point, and each row is going to represent the coordinate. So we already figured out that A was at -3, 0. So we're going to say that A is at -3, 0. Okay. B up here is at 0, 3. So if I put that into my matrix, B is at 0, 3. C over here is at 2, 1. Right? It's at 2, 1. And D down here is at -1, -1, -1. Yeah, -1, -1. All right, and so I can write that in here, -1, -1. So this is a way that we can write the coordinates for quadrilateral ABCD in a matrix. We don't have to write the outside part. This is really what we're looking for. We're looking for a matrix where the first row represents the x coordinates, the second row represents the y coordinates, and the columns represent a point in our quadrilateral. So you can imagine if we had, a polygon with 6 points, then we could have a matrix that was a 2 by 6 matrix, and each column would represent one of the 6 vertices. So again, seems a little bit weird, but it's actually going to help us out later. So we can represent points or multiple points, multiple vertices on our polygon by putting them into a matrix. So hopefully that makes sense to you. If not, try another example of that, okay? So one of the things I wanted to tell you with matrices, this is just a general property of matrices, it's not particular to what we're talking about translation, is that we can add and subtract matrices together. So this is actually really easy peasy. The only rule for adding and subtracting matrices is that they have to be the same size. Okay, so that's why I made a big deal in the beginning of knowing how big your matrix is, because if you want to add and subtract them together, they have to be the same size. So here are two matrices. This is a 2 by 2 and a 2 by 2. So I'm allowed to add them together, and it's actually really super duper easy to do. So if you have a 2 by 2 matrix and you're adding it to a 2 by 2 matrix, guess what? It makes a 2 by 2 matrix. And what you do is you literally add whatever is in the first row, first column, to whatever is in the first row, first column. So you're going to do 4 plus 1 equals 5. Okay, and then you're going to do whatever is in the first row, second column, and add that to the first row, second column. So -2 plus 2 is 0. Okay, 2 plus 5 equals 7. So see, easy peasy, right? And the last one's going to be -3 plus -6, and you're going to get -9. So voila, you have learned how to add a matrix together. So what you aren't allowed to do then is you could not, if I had 4, -2, 0, 3, that's a 2 by 2 matrix, and I asked you to add it to 2, 1, which this is a 2 by 1 matrix, I can't do this. First of all, like, how would you add it? Which one would you know to do? You don't know how to do that, right? So you can't do that, but you have to have them the same size. So that's the biggest thing with adding and subtracting matrices. Once you know that, the rest is easy peasy. If you want to know what the answer to B is here, if you want to try that, pause it and try it. It should be 4, 1, 10, -9, and 0, 7. Notice this one is a subtracting your matrices. So you're just going to do 7 minus 3 to get 4 and so on. So usually everybody has a pretty easy time with that. Okay, now why are we learning all this fancy matrix stuff other than to get us ready for Algebra 2? Let me give you an example of how we might use a matrice, another way to use translation by using a matrice. So if you watched 9.1, or when you watched 9.1, you remember you had your translation notation where you had xy translates to x plus 3, y minus 2, right? We also talked about using a vector, right? And where we had the vector notation with the two brackets around it to represent that. So another way that we could talk about using a translation is to actually have a matrix and then use a translation matrix to figure out where the new points are. Okay, so we're kind of combining all this information we have. So what's going on here is it says the matrix right here, this is a 2x3 matrix, represents triangle ABC. So what they're telling you is that, remember, this is your X, this is your Y, and column A, or the first column represents A, B, C. So these are coordinates, right? So before we even do anything, this matrix represents triangle ABC. So let's graph it. I better zoom out for that, right? Oh, sorry. So A is at 2, negative 3, right here. B is at 3, 2. And C is at 4, 0. So here is my original triangle ABC, and I know that that's my triangle because they're telling me this matrix represents that. So when you have a matrix, first row is always X, second row is Y, then you order the letters and whatever, they tell you triangle ABC. Okay, so now what they're telling me is find the image matrix that represents, so the image, remember, is the new image matrix that represents the translation of ABC, 4 units left and 1 unit down. Then graph ABC and its image. So again, lots of words, not too hard to do. And they're telling you over here, in order to add 2 matrices, they must have the same dimensions. So the translation matrix must have 3 columns, the polygon to match. So what's going on here is our original, our pre-image is at 2, negative 3, 3, 2, and 4, 0, right? This is our matrix right here. That's where our pre-image is that I just graphed over there, okay? And what they're telling you is that the image matrix, which, remember, it sounds a little confusing, but image matrix means the new matrix, is 4 units left, 4 to the left, and 1 down. Okay, so if I was going to write that in translation notation, I would say X, Y translates to X, and it's going 4 to the left. So that means X minus 2, Y is going 1 down, so Y minus 1. Right? When you're going to the left, it's negative. You're going down, it's negative. That would be how I would write it in translation notation. How I would write it in the component vector notation is I would write it as negative 4, negative 1. Right? Those, if you don't know what I'm talking about, go back to 9.1, and those are the 2 that we talked about for translation. Today, we're talking about how do we do that with a matrix. Well, if we're talking about a matrix and it's going 4 to the left, remember, our first row represents our X. So it's going negative 4 to the left, and it's going negative 1 down, right? Because that's, each column represents an X and a Y. So this is our translation matrix, okay? This is our translation matrix. Now, the other thing I just taught you was that your matrix, if you want to add it, if you want to translate something, if you want to add 2 matrices together, they have to be the same size. And this matrix right here is a 2x3 matrix. So guess what? This one has to also be a 2x3 matrix so that I can add it together. So basically, point A, I'm translating by negative 4, 1. Point B, I'm translating by negative 4, 1. And point C, I'm translating by negative 4, 1. So if I add my pre-image to my translation matrix, and I add those 2 together, what I'm going to get is my image matrix, or my new my new spot, right? So remember, when you're adding, you're going to end up with the same size matrices, plural, same size matrix, and you're just going to add the same position in each matrix. So it's going to be 2 plus -4 is going to give me -2. 3 plus -4 is -1. 4 plus -4 is 0. Then I'm going to move to my second row. So it's going to be -3 plus -1 is -4. 2 plus -1 is 1, and 0 plus -1 is -1. So this is my image matrix, and what this represents is this column is my A prime, this is my B prime, and this is my C prime. So each of those columns is going to represent my new image matrix. So the last point is just to graph it, right? And A is at -2, -4. Okay, that's my A prime. Remember, that's my image matrix. My B is at -1, 1, B prime. And my C prime is at 0, -1. Okay, so look what happens when you use your new translation matrix. So another way to do a translation, basically that's all this is. You've moved your pre-image is purple, your image is red, and have we moved 4 units left and 1 unit down? Well, let's check. To go from B to B prime, we've moved 4 units to the left and 1 unit down. So basically all that to say that this is a super fancy way of translating. Now, this does have a purpose because we are going to use matrices. What we're going to talk about on Wednesday is we're going to talk about reflections and rotations, and we're going to talk about that using matrices as well. So make sure that you understand this for translations because we're going to be using that for other things as well. As always, if you guys have any questions, feel free to reach out and enjoy your day. Bye, guys.